On the nights approaching December 19, 2025, telescope operators across 3 continents began reporting something unusual. A faint smudge in the southern sky was brightening ahead of schedule. More striking than the light itself was its color, a pale, unmistakable green, glowing softly against the black. This was not the dusty yellow-white of a familiar comet. This was, chemistry speaking, the green hue signaled diatomic carbon, Ca, breaking apart under ultraviolet bombardment from the sun. It was a signature, not an ornament, and it was changing in real time. The object had a catalog designation, 3A Atlas. The 3A prefix is reserved for interstellar visitors, bodies confirmed to have originated beyond our solar system. This was only the 3rd such object ever recorded. Unlike Onai Oumuamua, which revealed itself only in departure, and 2A Borisov, which behaved predictably, 3A Atlas was offering something richer, a chemical performance unfolding under direct observation. Its coma, the diffuse cloud of gas and dust surrounding the nucleus, was evolving night by night. Brightness curves bent upward. Jets flickered on in scattered bursts. And every photon captured was irreplaceable, because this object was on a hyperbolic trajectory. It would never return. Every measurement was a once-only chance. What made this moment scientifically urgent was not spectacle, but constraint. Interstellar objects pass through our planetary neighborhood so rarely that each encounter functions as a natural experiment, a sample delivered from another star system, offering evidence of conditions we cannot yet visit. But the evidence is ephemeral. Within weeks, 3I Atlas would recede beyond the practical reach of most ground-based instruments. The window for spectroscopy, astrometry, and high-resolution imaging was narrow. And the central question driving every observatory campaign was not simply what this object was, but what exact conditions, temperature, pressure, radiation environment, timescale, could have produced a comet arriving at 58 kilometers per second with a coma dominated by carbon dioxide. If you find yourself drawn to investigations like this, where faint light becomes forensic evidence and cosmic motion encodes origin, subscribe for more stories from beyond the solar veil. The timeline begins on July 1, 2025, when the Minor Planet Center received the first formal report of a fast-moving object in retrograde orbit. The discovery was credited to the Asteroid Terrestrial Impact Last Alert System, ATLAS, a robotic survey designed to detect near-Earth threats. But as often happens in modern astronomy, the true discovery was older. Pre-discovery detections were recovered from archival survey frames dating back to mid-June 2025. The object had been passing through our sky for weeks before anyone noticed it was not bound to the sun. Orbital determination takes time. Early solutions are provisional, refined iteratively as more positions accumulate. But by late July, the numbers had converged, and they told a story that no amount of perturbation analysis could undo. The eccentricity was measured at approximately 6.1, far beyond the parabolic threshold of one that separates bound from unbound orbits. Perihelion, the closest point to the Sun, occurred in late October 2025 at a heliocentric distance of roughly 1.36 astronomical units, just beyond Earth's orbit, inside the orbit of Mars. The inclination was measured at approximately 175 degrees, meaning the object was traveling in the opposite direction to the planets, cutting through the ecliptic plane at a steep angle. And the hyperbolic excess velocity, the speed retained after escaping the Sun's gravitational influence, was calculated at roughly 58 kilometers per second. These are not ambiguous figures. They exclude capture scenarios. They exclude long-period comet misidentification. This object originated in interstellar space, and it would return there. The orbit was not a metaphor. It was a fingerprint. The encounter geometry added practical urgency. Closest approach to Earth would occur on December 19, 2025, at a distance of approximately 1.8 astronomical units, roughly 270 million kilometers. That is far by terrestrial standards, but close enough for moderate aperture telescopes to resolve structure in the coma and track brightness variations with precision. Perihelion had already passed by the time of Earth's closest approach, meaning the comet was warming, outgassing, and potentially fragmenting as solar heating penetrated deeper into its nucleus. The observation window was defined not by convenience, but by physics. Sunlight drives activity, and activity produces the signals we measure. Orbital geometry was the first clue to where this object came from. Composition would be the clue to how it formed. Astronomy is a distributed enterprise. No single facility commands a complete view. Instead, data accumulates across observatories, wavelengths, and time zones, each instrument contributing what it can resolve. For 3E Atlas, the observational campaign was global, layered, and deliberately redundant. Discovery surveys like Atlas operate by repeatedly imaging large patches of sky, comparing frames taken hours or nights apart, and flagging anything that moves or brightens. Their strength is coverage, not detail. Once an object is flagged, follow-up assets take over. For 3E Atlas, these included the Panoramic Survey Telescope and Rapid Response System, PanSTARRS, and other robotic networks capable of refining the orbit and monitoring photometric behavior. But ground-based observations face limits: atmosphere, weather, scattered light from the moon. To push deeper, space telescopes were mobilized. The Hubble Space Telescope was tasked with morphological characterization. Hubble does not see in the infrared where molecular emission lines are most diagnostic, but it excels at resolving spatial structure. Images captured in visible wavelengths revealed a classic cometary morphology, a bright central condensation surrounded by a diffuse coma extending tens of thousands of kilometers, with faint asymmetries suggesting non-uniform outgassing. Dust tails formed and evolved as radiation pressure from the sun pushed particles outward. Hubble's precision photometry allowed researchers to place upper limits on the size of the nucleus, though the true diameter remained uncertain, obscured beneath the bright coma. The best estimates hovered in the range of a few kilometers, consistent with small solar system comets, but the error bars were wide. The James Webb Space Telescope contributed something Hubble could not: chemical specificity. JWST's infrared spectrometers can detect vibrational and rotational transitions of molecules in the coma, effectively fingerprinting the composition of the gas being released. Early spectroscopic observations revealed strong emission bands consistent with carbon dioxide, water vapor, carbon monoxide, and various organic dust components. What stood out immediately was the ratio. Ka appeared to dominate the volatile budget, with the Ka-to-Ocho ratio described as among the highest observed in any comet, interstellar or otherwise. This was not a trace contaminant. It was the primary driver of activity. Meanwhile, other assets contributed temporal and geometric context. The Transiting Exoplanet Survey Satellite, TESS, normally used to detect planet transits, was repurposed to monitor 3E Atlas for rapid variability, potential evidence of rotation, fragmentation, or explosive outbursts. Ground-based spectroscopy campaigns tracked emission line strengths night by night, watching for changes in gas production rates as the comet's spin brought different regions into sunlight. Amateur astronomers, working with backyard telescopes and charge-coupled device cameras, stacked long exposures to pull faint structure out of the noise. Their images, often dismissed as less rigorous, provided continuity. Professional time is precious and allocated in small blocks, but amateurs observe nightly, compiling light curves that reveal trends invisible in sparse datasets. Yet even with this orchestrated effort, disagreements emerged. Photometry from different observers sometimes diverged by several tenths of a magnitude. Tail morphology appeared to shift between epochs, not smoothly, but in jumps. Some of this was instrumental: different filters, different calibration pipelines, different assumptions about the point spread function versus extended coma emission. But some of it was real. The object was changing, not just moving. To understand what was seen, one must first understand what a comet does. At its core, a comet is a frozen reservoir. Water ice, carbon dioxide ice, methane, ammonia, and complex organics bound together in a porous, fragile matrix. When solar radiation heats the surface, volatile ices sublimate directly from solid to gas, expanding rapidly and dragging dust grains along. This mixture forms the coma, a temporary atmosphere with no confining gravity, bleeding mass into space at meters per second. Sunlight ionizes some of the gas, creating a plasma tail that streams away along magnetic field lines embedded in the solar wind. Meanwhile, radiation pressure pushes dust particles outward, forming a separate curved tail whose shape depends on particle size and ejection velocity. This is the standard model. For 3A Atlas, the standard model held, mostly. But the details mattered. JWST's detection of a COV-dominated coma was the defining observational result. Carbon dioxide sublimates at temperatures slightly lower than water ice, around 150 to 180 Kelvin, under vacuum conditions. In a comet nucleus, CO can be trapped as clathrate inclusions within water ice, or it can exist as distinct layers or pockets formed under different thermal histories. The high CO-to-Ho ratio suggested either that the formation environment was cold enough for CO to condense abundantly, or that the surface had been processed, perhaps by cosmic ray bombardment or stellar radiation, in ways that preferentially removed lighter volatiles, leaving con-rich layers exposed. The green glow, meanwhile, pointed to diatomic carbon. Ca is not a primary ice component. It forms when larger carbon-bearing molecules, hydrocarbons, perhaps cyanogen, or other organics, are photodissociated by ultraviolet light. The intensity of the green emission scales with both the production rate of parent molecules and the solar flux, which increases as the comet approaches the Sun. Observers reported that the green hue strengthened through November and December, consistent with rising activity post-perihelion dawn. This was expected. But what was less expected was the rapidity of the brightness changes and the asymmetry of the outgassing pattern. Quantifying the scale requires precision. At perihelion, 3 Atlas was approximately 1.360 from the Sun, about 204 million kilometers. At that distance, solar heating is strong enough to sublimate water ice from sunlit surfaces, but not uniformly. If the nucleus is rotating, only a fraction of the surface is illuminated at any given moment. If volatile ices are unevenly distributed, concentrated in specific regions or beneath insulating dust layers, then outgassing occurs in localized jets rather than a smooth isotropic flow. These jets can be detected as brightness enhancements in the coma, asymmetries in the dust tail, and even as non-gravitational forces that gently alter the orbit. The green emission itself is a diagnostic. The CA Swan band system emits strongly in the 470 to 560 nanometer range, peaking around 516 nanometers. The intensity depends on the column density of parent molecules and the solar ultraviolet flux. During December 25, as 3 Atlas moved through its closest approach to Earth, observers noted night-to-night fluctuations in the green signal, suggesting either rotating active regions or episodic bursts of gas release. This variability tied directly to the central question: what exact conditions, composition, structure, thermal history, could produce a comet where Ku drives the show, and organic photoproducts glow green as it passes the inner solar system for the first and only time? The phrase exact conditions is not poetic license. It is a scientific framework. Formation temperature determines which ices condense. Radiation exposure determines which molecules survive. Ejection dynamics determine arrival velocity. Each observable orbit, spectrum, brightness, color constrains one or more variables. Together, they map backward to an origin. Yet the map was not without contradictions. Cometary orbits are rarely perfect Kepler ellipses. Outgassing produces thrust. When jets of gas stream from a rotating nucleus, they impart a torque and a net force, nudging the orbit in ways that pure gravity cannot explain. These are called non-gravitational accelerations, and they are routine in solar system comets. For 3E Atlas, orbit refinement teams reported small but measurable deviations from a purely gravitational trajectory. The deviations were consistent in magnitude with Coulomb-driven jets, and the timing correlated with increased brightness, evidence that outgassing and orbital perturbation were linked. But consistency does not mean simplicity. Different observers, working with slightly different datasets, derived slightly different non-gravitational parameters. Some solutions required radial acceleration, force directed toward or away from the sun. Others required transverse components, forces perpendicular to the radial direction, suggesting asymmetric jetting from a rotating nucleus. The ambiguity was not a failure of measurement. It was a consequence of incomplete sampling. The comet was rotating, evolving, and observed from a constantly shifting vantage point. Disentangling rotation, precession, and jet geometry required more data than the brief observation window provided. Until complex. Then there were the photometric anomalies. Brightness measurements from different instruments sometimes disagreed by more than the stated uncertainties. Some of this could be attributed to filter differences, broadband photometry averages over wavelengths, smoothing out spectral features. But some images showed the coma appearing brighter or more compact than predicted, then dimming or expanding unexpectedly days later. Tail orientation, too, proved puzzling. Dust tails should lag behind the comet's motion, swept back by radiation pressure at a calculable angle. Yet in some images, the observed tail angle deviated slightly from the model. The deviations were small, a few degrees at most, but persistent. One explanation was dust size distribution. Radiation pressure acts more efficiently on small particles. If the size distribution was skewed, more large grains than typical, perhaps due to fractal aggregation or incomplete fragmentation, then the tail would appear straighter, less swept. Another explanation was observational timing. Dust tails evolve over days. An image captured hours after a sudden burst of dust production might show a tail that had not yet settled into equilibrium geometry. The green emission added another layer. Its intensity varied not just with heliocentric distance, but with phase, evidence that the illuminated fraction of the coma was changing as the comet rotated. If the rotation period was short, hours rather than days, then the observed brightness could oscillate as active regions spun in and out of view. But determining the rotation period required continuous monitoring, and most facilities could observe only a few hours per night. Gaps in coverage introduced ambiguity. Peaks and troughs in the light curve could be aliased, misinterpreted, or lost entirely. The discipline here is critical. An anomaly is not proof of the exotic. It is an invitation to refine the model. Comets are complex, messy, heterogeneous objects. They rotate, they fragment, they outgas in bursts. Most anomalies resolve when the model includes rotation, dust properties, and realistic thermal physics. The question is not whether conventional physics can fit the data. It almost always can, but what the fit requires. What are the implied properties? What are the boundary conditions? And once we know those, what do they tell us about the object's birth? For 3 Atlas, the implied properties pointed toward a formation environment colder and more carbon-rich than the inner regions of our own protoplanetary disk. Carbon dioxide ice is stable at temperatures below about 80 Kelvin under typical interstellar pressures. For QH to dominate over water, the comet either formed in a region where temperatures rarely exceeded that threshold, or it formed in a disk with an unusual carbon-to-oxygen ratio. Perhaps around a star with different metallicity, or different balance of refractory versus volatile material. Radiation processing adds nuance. If the object spent significant time drifting through interstellar space before entering our solar system, cosmic rays and ultraviolet photons from the galactic background would have bombarded its surface, breaking chemical bonds and driving volatile loss. Lighter molecules, hydrogen, helium, methane, would preferentially escape, while QE, locked in ice, might remain. This could explain why the coma was con-rich. Not because water was never present, but because surface layers had been stripped away over millions of years, exposing deeper, less processed ice. Another factor is collisional history. If the object originated in a planetary system around another star, it might have been ejected by gravitational interactions with giant planets. Such ejections are violent, often accompanied by collisions or close encounters that fracture and compress the body. Fractures create pathways for gas to escape more easily once the object is warmed. Compression can stratify volatiles, concentrating certain ices in pockets or layers that sublimate only when exposed to direct sunlight. These are all conventional astrophysical mechanisms: temperature, radiation, gravity, collisions. They are the baseline explanations, the scaffolding upon which any interpretation must be built. But they are not the only ideas circulating. Some researchers have argued for more speculative interpretations. Avi Loeb, director of the Galileo project, has suggested that certain interstellar objects might be technological in origin, fragments of artificial structures, probes, or debris from advanced civilizations. For Oumuamua, Loeb pointed to the object's extreme elongation and non-gravitational acceleration as potential evidence of a solar sail. For 3A Atlas, no such claim has been formally published, but the pattern of brightness variability and the presence of non-gravitational forces have been noted in public discussions as consistent with directed or controlled behavior. This must be stated carefully. There is no direct evidence of technology. The observed behavior, brightness changes, outgassing, non-gravitational acceleration, is fully consistent with natural cometary physics. Co-sublimates. Dust scatters light. Jets produce thrust. Every feature can be explained without invoking artificial intervention. The burden of proof for an extraordinary claim is correspondingly high. One would need to demonstrate emission patterns inconsistent with thermal equilibrium, propulsion signatures that cannot be explained by sublimation geometry, or maneuvers decoupled from solar heating. None of these have been observed. Yet the hypothesis is not scientifically useless. It is testable. If future observations revealed collimated beams of light, narrowband radio transmissions, or trajectory adjustments occurring in shadow where no solar heating occurs, then the technological interpretation would gain ground. Until then, it remains speculative, a boundary case useful for sharpening definitions. What would an artificial object actually look like, and how would we distinguish it from a comet? The value of 3I Atlas lies not in its strangeness, but in its specificity. Even if entirely natural, it functions like a returned sample from another star. Its chemistry preserves a record of the temperature, pressure, and radiation environment in which it formed. Its orbit encodes the dynamics of its ejection, and its behavior under solar heating reveals the internal structure built up over billions of years. This is forensic astronomy, reading history from light. The investigation is not finished. As 3I Atlas recedes from the Sun, its activity will decay. If Co dominates, sublimation may persist longer than for a water-driven comet, extending the observation window. Ground-based campaigns are tracking the light curve, watching for the inflection point where gas production drops and brightness begins its final decline. Spectroscopy continues, targeting weaker emission lines that become detectable as the coma thins. And astrometry, precise position measurement, continues to refine the orbit, reducing uncertainty in the hyperbolic excess velocity and improving the backpropagation that estimates where the object came from. One of the next major waypoints is the comet's outbound passage through the orbital region of Jupiter in 2026. Though the comet will not pass particularly close to the planet, the gravitational influence is sufficient to perturb the trajectory slightly. Measuring that perturbation provides an independent check on the object's mass and helps constrain the orbit solution. More importantly, continued tracking through 2026 and beyond will reveal whether the non-gravitational accelerations are consistent with a single outgassing model or whether they require additional parameters: rotation, axis precession, discrete outburst events, or fragmentation. Predictions become tests. If QO-driven activity persists beyond 2 AU, brightness should remain elevated longer than models calibrated to water ice comets predict. If dust production collapses as the comet cools, the optical brightness will drop faster than the gas emission, and the coma will shift from dusty white yellow to a pure gas glow. If the rotation period is short, photometric variability should remain detectable, even as the comet dims, allowing observers to track how spin and outgassing interact over months. Global campaigns are coordinating these observations. Telescope networks synchronize observations to minimize gaps. Spectroscopists share data to cross-calibrate line strengths. Modelers ingest the measurements, and iterate, adjusting thermal models, dust properties, and jet orientations until the synthetic light curve matches the real one. Each iteration tightens the constraints. Each constraint narrows the space of possible origins. And yet, humility remains. This is the third confirmed interstellar visitor to enter our solar system in recorded history. The first, Oumuamua, defied easy classification. No coma, no tail, an elongated shape, and non-gravitational acceleration, with no detected outgassing. The second, Tuai Borisov, was comfortably comet-like, familiar, almost predictable. Now 3I Atlas offers a third data point. A comet, yes, but one whose chemistry stands apart, whose cone dominance forces us to reconsider what normal means in the broader galaxy. We do not know how common such objects are. We do not know whether our solar system's comet population is representative or an outlier. We do not know how many interstellar wanderers pass through undetected each year, too faint or too fast for our surveys. What we do know is that each one is a natural experiment, a probe sent from a stellar system we cannot visit, carrying information encoded in ice and motion. The exact conditions that shape 3 Atlas are not yet fully resolved, but they are measurable. They live in the orbit that traced its arrival, in the spectrum that maps its composition, in the brightness curve that tracks its response to sunlight, and in the subtle forces that nudge its path. These are not mysteries in the poetic sense. They are unknowns in the scientific sense, and unknowns can be constrained, tested, and eventually understood. The green coma will fade. The trajectory will carry the object outward, past Jupiter, past Neptune, into the dark. In a few years, no telescope will resolve it. In a few decades, it will be farther from the sun than Voyager. In a few centuries, it will be indistinguishable from the interstellar medium, anonymous again. But the data will remain. The measurements are permanent. And the questions they raise about formation, ejection, drift, and the diversity of objects born around other stars will guide the next observation, the next discovery, the next visitor. That is the humility and the wonder. We do not yet know all the answers, but we know how to ask the questions. And the universe sometimes replies.